Hello everyone, welcome to my YouTube channel. Today we'll be discussing simple harmonic oscillator. So before we go to simple harmonic oscillator, we should remember oscillators are the basic building blocks of waves. Without oscillator there will be no waves. So what is this oscillator? Let us first try to understand that thing. Consider a block with mass m, just as shown here. Mass m, this block has mass m. Okay, free to slide on a frictionless air track. This is the frictionless air track. Okay, this one, but attached to a light spring with its other end attached to a fixed wall. So this is the block, and it is attached to a fixed wall with a light spring whose what do we mean by light? That means we can skip the weight of the spring. Clear? Now what is happening here? The system has only one relevant degrees of freedom. And what is degrees of freedom? In general, the number of degrees of freedom of a system is the number of coordinates that must be specified in order to determine the configuration completely. That means if we say a point in space, three-dimensional space, it has a 3 degrees of freedom. Okay, it have 3 independent coordinates, so it has a 3 degrees of freedom. Let us say we are talking about 2 points connected with a line. Now for this, each atom has a 3 degrees of freedom, but as for this one, 1 degrees of freedom will be compromised. It will be common for both atoms or both point. So that's why it has a total of 2 into 3 minus 1 equal to 6 minus 1 equal to 5. These will be the degrees of freedom. And this one thing that is connecting these 2 points, this is called constraint. So the main discussion here is not about degrees of freedom. We just know about degrees of freedom. Let us come back to our main thing, that is harmonic oscillation. So in this case, because the spring is light, we can assume that it is uniformly stretched from a fixed wall to the block. Then uh, the only important coordinate is the position of the block. That means how much distance it has from this fixed wall. Let us say this is x0 at the beginning. In this situation, gravity plays no role because it will be cancelled out by the resultant force or reaction force. Okay, reaction force given by the track, it will be cancelled out. So from this we can conclude that gravitational force is cancelled by the vertical force from the track. The only relevant force that acts on the blocks come from this spring. Okay, by stretching or compressing the spring, the only relevant force come from this. When the spring is relaxed, there is no force on the block and the system is in equilibrium, that is the position is x0. Now Hooke's law tells us that the force from the spring is given by a negative constant minus k. This is the spring constant. Time of displacement, that is f equal to minus K into displacement, that is the force acting. Thus, if the position of the block at some time is x and the equilibrium position is x0, then the displacement can be taken as x minus x0. So f will become minus k x minus x0. Clear? So let us take this as a equation number 1. So let us make it happen. We're going to the next page. So we have what we have. We have here that if equal to minus k x minus x0. This is the equation number 1, or let us say only 1. Okay, this is our equation number 1. Now the constant k is called the constant k is called spring constant. Okay, it has unit. What will be the unit? Let us say for if we take force, what will be the unit of k? K equal to, actually very easy, F by x, Newton per meter. So Newton per meter is the unit of k. Unit of k is Newton per meter, that is force per unit length. That's how we define k. And if we talk about the dimension, that will be like this: dimension of k, dimension of force, that is ml t to the power minus 2, and dimension of the displacement, that is this. So what we get? We get m t to the power minus 2. So this is the dimension of spring constant k. Now we can always choose to measure the position of x of the block with our origin at the equilibrium position. That means we can take x0 as 0 position, that is the origin. Okay, so equation number 1 will become, how it look like? It look like f equal to minus kx. Okay, so this will be the our second equation. This is the form that we should remember about spring constant. X is the displacement, k is the spring's constant, and F is the restoring force, or the force on the block that takes the block back to its equilibrium position. Now, harmonic oscillation results from the interplay between the Hooke's law force and Newton's law, F equal to ma. Okay. Now, harmonic oscillation results from the interplay between interplay between Hooke's law, force, and Newton's law, Newton's law, that is F equal to ma. Now let x be the displacement of the block as a function of time. Then Newton's law implies let x be the displacement of the block as a function of time, as a function of time t. Then the Newton's law look like then Newton's law look like m d2x dt2. d2x dt2 is the acceleration equal to minus k x t. Okay, by combining this thing and this thing. Clear? This can be taken as equation number 3. Okay, so where we are getting an equation of this form, that is m d2x dt2 equal to minus kx. Okay, but also its derivative is called a differential equation. So we are getting an equation of this form involving not only the function x but also its derivative is called a differential equation. The differential equation 3 is the equation of motion for the system that is shown in the figure, or the spring system. Because the system has only 1 degrees of freedom, there is only one equation of motion. In general, there must be one equation of motion for each independent coordinate required to specify the configuration of the system. That means if the degrees of freedom is 3, we have to give 3 equation of motion. The most general solution to this differential equation, the most general solution of equation 3 is xt equal to a cos omega t plus b sin omega t. Okay, this is the actually solution for the differential equation, double differentiation equation, where omega equal to root over k by m is a constant, is a constant with unit of t minus 1, that is second inverse, called angular frequency, angular frequency. Okay, now the angular frequency will be very important quantity in our study of wave phenomena. We'll almost always donate it by the lowercase of Greek letter omega. Okay, this is called omega. Now, because the equation involves a second time derivatives but not higher derivatives, the most general solution involves two constants. This is just what we expect from the physics, because we can get a different solution for each value of the position and velocity of the block at the starting time. Generally, we'll think about determining the solution in terms of position and velocity of the block when we first get the motion started at a time that we conventionally take to be t equal to 0. For this reason, the process of determining the solution in the terms of position and velocity at a given time is called initial value problem, is called initial is called initial value problem. Now the value of position and velocity at t equal to 0 are called initial condition. For example, we can write most general solution for equation number 4, in terms of x0 and x test 0. The displacement and velocity of the block at time t equal to 0, setting t equal to 0 so x x0 equal to হচ্ছে displacement x dash 0, এটাকে this one will be velocity. Okay, so equation 4 look like t equal to 0. So xt will look like, how it look like, it will look like x0 cos omega t plus 1 by omega x dash 0 sine omega t. Okay, these are the from.